In this video lesson, we are now going to look at classifying particles as hadrons, baryons, mesons, leptons, or bosons. And then we're going to recall that the standard model classifies matter into quarks, leptons, and bosons. There are different ways of classifying particles. The first way is according to the forces they feel between them. So hadrons feel the strong force and the weak force, whereas leptons feel the weak force but don't feel the strong force. Note that all particles, including the massless particles like the photon and neutrinos, are affected by gravity. And the reason for that is because gravity, according to Einstein's theory of general relativity, is in actual fact the curvature of space-time. So when you place a mass into space-time, which is the three dimensions of space and the extra dimension of time, then it bends or curves space-time. So albeit that these particles are tiny, they would still curve space-time. And all charged particles are affected by the electromagnetic force. Example, protons, electrons, and quarks. Looking at baryons or baryons, we see that there are different categories. We have the protons, which are made up of 2 ups and 1 down quark, and its antiparticle, which would be made up of 2 anti-up quarks and 1 anti-down quark. We see that the rest mass here is relatively high, 938,3 mega electron volts per speed of light squared. They have a baryon number of +1 for the proton and -1 for the antiproton, and they are very, very stable. Protons don't just decay. Then we have the neutron. As we have learned, it's made up of 1 up and 2 down quarks, and its antiparticle is made up of the antiquarks anti-up and 2 anti-downs. They both have the same rest mass, and we can see here that the neutron, as we have discussed before, is slightly heavier. It too has a baryon number of +1 for the neutron and -1 for the antineutron. We then also get the lambda. We can see the lambda is heavier, and the lambda consists of an up, a down, and a strange quark. We can call that the lambda 0. And we can see that it is very unstable. We can see that it is 2,63 times 10 to the minus 10 seconds. Then we get the sigmas. You've got the sigma plus, the sigma 0, and the sigma negative, and you can see they are made up of different combinations. 2 ups, 1 strange, an up, a down, a strange, 2 downs and a strange quark, and then of course the antiparticles are made up of the antiquarks. We can see they are getting increasingly heavier, but at the same time they are very, very unstable. Then you get the chi, which is also extremely unstable. You get the chi 0 and the chi negative, and the two, they're made up of ups and 2 strangers, or downs and 2 strangers. And then you also get the omega minus and the omega plus. They are antiparticles of each other, and you can see they are very, very heavy. They all have baryon numbers of +1 for the particle, and the antiparticle have baryon numbers of -1. But there are many other baryons that are known, and these particles all form part of what particle physicists tongue-in-cheek call the particle zoo. And now we look at the mesons, which are 2 quark systems. So we have the pi mesons, or the pions. We have the pi plus and its antiparticle pi negative. We see that they're made up of an up and an antiquark down. And then we've got the pi minus, which is made up of the antiquark up and the down quark. We see they have rest masses of 139,6 mega electron volts per speed of light squared, also unstable. We have the pi 0, which is its antiparticle. And what's interesting here, together with the eta 0, is that they are made up of different mixtures of the up, anti-up, and down, anti-down, and depending upon the nature of the mixture determines whether it is a pion or an eta meson. Now, remember, these mixtures is not a classical mixture. This is to do with quantum mechanics, and quantum mechanics by its very nature is strange. And so we talk about superpositioning of states and that in quantum mechanics. So this goes way beyond AP physics into advanced quantum mechanics. And we see here that we've got K plus and K minus, which are made up of an up quark and an anti-strange, and the opposite for the K negative. The K0 or the kaon, which is made up of a down and a strange quark, so you can think of a kaon as a K meson, and the anti-quark K0, which is anti-down quark and a strange quark, and here too the eta is the antiparticle of itself. Very, very heavy particle, and we see that's extremely unstable. There are many other mesons that are also known. Note that the baryon numbers are 0. A second way of classifying elementary particles is according to their intrinsic spins. So we have fermions, and fermions are particles with half integer values of their intrinsic spin. So we've already learned that electrons have a plus half spin. If they're in an orbital, then they would have a plus half and a negative half to obey Pauli's exclusion principle. We also know that quarks have got plus a half spins. Pauli's exclusion principle is something we've encountered already. We encountered in grade 10 physics when we did the Aufbau diagrams, and where we had to place electrons in orbitals, and those electrons had to have opposite spins. So examples are electrons and quarks. Bosons, on the other hand, are particles with a 0 or integer value of intrinsic spin, and they do not obey the Pauli exclusion principle. Examples are W and Z bosons, as well as the Higgs boson, which we know is the God particle. And the fact that bosons do not obey Pauli's exclusion principle is actually used to advantage to produce a fifth state of matter called Bose-Einstein condensates, as well as superfluids, where particles can occupy the same state and actually become like a giant quantum system with unusual properties like liquid helium being able to flow without any hydrodynamic drag. In the case of leptons, these are particles not affected by the strong force, but they are affected by the weak force, and examples of leptons are quarks and electrons. So now we look at the leptons, and we're going to look at a table that consists of a wide variety of leptons. So starting off with the electron and its antiparticle, the positron, we see there's the E minus and the E positive. They have a rest mass of 0.511 mega electron volts per speed of light squared. We see that they are stable, and because they're not baryons, all of these leptons will have a baryon number equal to 0. Now, the electron neutrino is designated with the Greek letter nu, not mu, but nu, with a subscript E, and its anti-electron neutrino is with the bar on top. And it was thought that neutrinos don't have a rest mass, but we see in this table that they have a rest mass of 7 electron volts, which is tiny in comparison to the rest of them, which have masses, rest masses in the region of mega electron volts per speed of light squared. Now, the neutrino interacts by means of the weak nuclear interaction, and it is the strength of the interaction is so weak that an electron can pass through the Earth without interacting with a single particle in the Earth. So they are quite elusive particles that were very difficult to actually discover experimentally. Now we look at the muons. So the muons, we use mu for the mu lepton, muon, mu minus and mu plus. They have a much higher rest mass. And we then have the neutrino, the muon neutrino, and its antiparticle. And we can see here with the neutrinos also very, very, very small masses, rest masses. We then have the tau lepton, which is an exceptionally large, exceptionally heavy lepton in comparison to the other leptons, like the electron and the muon. And in a way, the tau is actually the heavy partner of the electron. And it too has an associated neutrino. This is the tau neutrino, and it also has a very, very low rest mass. Now, if we look at the charges, we'll see that the electron, as we know, is assigned a charge of -1, and the positron +1, and that 1 is actually a relative scale of equivalent to 1,619 times 10 to the -19 coulombs. We see that the charges of the electron neutrino and its antineutrino is 0. When we look at the muons, they have the muon negative has a charge of -1, the same as an electron, and the muon positive is +1. There too, the muon neutrinos also have a charge of 0. We then see the tau minus and the tau plus. They have charges of -1 and +1, and the associated neutrinos also have a charge of 0. So we see a pattern here where we have very light leptons, the electrons, with the associated neutrino and antineutrinos. Then we have the heavier muon with its antiparticle, with its associated neutrinos. And then we have the heavy lepton and its antiparticle, the tau, with its associated neutrinos. So we see there's a pattern here. Now, looking at lepton numbers, we have the electron lepton number, the muon lepton number, and we have the tau lepton number. And these are in essence family numbers. And if we use capital L for the lepton number, we see that the electron is assigned 1 for its lepton number, as is the negative muon and the negative tau. And their antiparticles have lepton numbers -1. And then when we look at the neutrinos, the electron neutrinos also assigned a lepton number of 1, as are the other neutrinos, the mu neutrino and the tau neutrino, and their antiparticles are assigned -1 for the lepton number. So looking at this table, we've now got a nice summary here. We can see that there's the baryon number, or baryon number, that some people pronounce, and that's 0. But then we've got the electron lepton numbers, the muon lepton numbers, and the tau lepton numbers. And we can see that as the leptons get heavier, they become way more unstable. We can see that the lifetime of a muon is only 2,2 times 10 to the -6 seconds, whereas the heavier tau is 2,91 times 10 to the -13 seconds, which is a much, much, much shorter lifespan or lifetime. So the Standard Model is one of the great successes of modern physics. And what it does is it classifies all the elementary particles either as quarks, leptons, or bosons. There are 6 quarks and there are 6 leptons. And the bosons are what they call the exchange particles or the force carriers. And we'll learn more about them when we study the 4 forces, 4 fundamental forces later on in this course. So here is a nice table that summarizes the Standard Model. We've got the 6 quarks. We've got the up, the down, the charm, the strange, the top, and the bottom. And these quarks are all fermions, which are matter particles, and they have a spin of a half. Then we have the leptons, which we have just learnt about, the electron and the electron neutrino, the muon and the muon neutrino, the tau and the tau neutrino, and they too are also fermions, which have a spin half. On this side here, we have the bosons, and they are the force carriers. We have the gluon, the photon, the Z boson and the W boson, and then we have the famous Higgs boson, which was recently proven to be in existence at the Large Hadron Collider. But the gluon is associated as the force carrier for the strong nuclear interaction, which is often known as or also known as the gluonic force. We have the photon, which is the force carrier for the electromagnetic force. We have the Z boson and the W boson, which are the force carriers for the weak nuclear interaction. The force carrier or the proposed force carrier for gravity is known as the graviton, but that is yet to be proven experimentally and hence doesn't form part of the standard model. So all of these particles here, all these fermions, these matter particles, have got antiparticles which have the same mass, but they have opposite charge. And these bosons here are known as gauge bosons, and the Higgs boson is known as a scalar boson. And as has been mentioned, we will be looking at this in more detail at a later stage in this course.